This is the second presentation in my series on science and creationism. And just to mix things up, I thought I wouldn't actually talk about evolution today, but instead start at the very beginning, of the universe that is, and talk about cosmology. I've also folded in some criticisms from the first presentation, so I'll try not to record things when I have a cold in future, and I've turned up the volume a bit. Right, let's get started. Cosmology is a science which covers the universe at large scales, looking at things that are very old, very far away, and often very bizarre. Of course, cosmology has nothing to do with evolution at all, but it's so often included in the creationist debates that it's worth covering here. After all, if a creationist wants to claim that the entire universe is 10,000 years old, then that goes against all of cosmology too. After all, the nearest large galaxies are millions of light years away, which means that the light we're seeing from them now left them millions of years ago. And that's the very nearest ones, which is practically in our backyard compared to the kinds of objects that cosmologists study regularly. I'm going to cover other aspects of astronomy in later presentations, so for anything on stars and galaxies and planetary science, please watch this space. Essentially, I'm covering the universe in age order. I probably shouldn't be starting with cosmology. It's a notoriously mind-bending subject. If you haven't studied it at university level, then you might be forgiven for thinking that you understand it. If you have studied it at university level, then you'll definitely know that you don't understand it. Unless, that is, you've been working on it for the last 30 years or so, in which case you probably understand quite a lot of it, but not all of it. Nobody understands cosmology entirely. The more you understand about cosmology, the more you'll agree with this statement. Please don't rely on intuition or any simplified models you may have read, unless you really know what you're talking about. Sadly, this is one topic where I suggest you just learn the answers to the common questions, read around them a bit, and then move on. Let's start at the very beginning with the Big Bang. I find that this is a really misunderstood topic, though it's hardly surprising. For a start, the event it describes was physically the smallest thing ever to happen in the universe, so hardly big. And secondly, there was no bang either, at least not in the way we would conventionally think of it. Let me back up a bit. What exactly is the Big Bang Theory, and where did it come from? We know that the universe is expanding. We know this because we can see pretty much all the objects in it moving away from us with speeds that vary with their distance from us. And we know they're moving away from us because we can measure it. Galaxies are made up of billions of stars, and stars burn through a process that is very well understood. And because we understand what's going on in stars, we can work out what the average star should look like. And if we can work out what one star should look like, we know what billions of them should look like together. That's all well and good, but what then happens when you have a galaxy of billions of stars moving away from us at a very high speed? And by that I mean thousands of kilometres per second. You know when you hear an ambulance with a siren going past you at high speed, the pitch of the siren suddenly drops as soon as it's moving away from you. This is due to a feature of physics called the Doppler effect. In this case it's sound waves, but the same thing can happen with light if you get fast enough. The frequency of sound waves affects the pitch of the sound. When an object is moving away, the sound waves are stretched out, so the pitch is lower. In the case of light, the frequency affects colour. So when a galaxy is moving away at a very high speed, it appears redder than it ordinarily would do. We can measure how much redder it appears to be, and that tells us directly the speed at which that galaxy is moving away from us, and that's known as redshift. So, as I said, all galaxies sufficiently far away from us are moving away. The further away they are, the faster they're moving away. This has been known since the 1920s, and the first person to write down this relationship was Edwin Hubble, after whom the Hubble Space Telescope is named. The obvious conclusion is this. If all galaxies are moving away from one central point, then if you start looking back in time, it must be possible to trace them all back to the point where they were all at the same location. As it turns out, this time is the age of the universe, around 13 billion years, and that single event is known as the Big Bang. Please note that the fact that all galaxies appear to be moving away from us doesn't mean that we're at the centre of the universe. Because of the geometry of this expanding universe, it would look this way no matter where you observed it from. The science of the Big Bang is not well understood. When you start trying to cram all the matter in the universe into a smaller and smaller space, then the density increases, the temperature increases, and physics starts to get very, very strange indeed. But this is the cutting edge of cosmology. Scientists are working on theories to understand what was happening in the first few seconds or microseconds or even less of the universe. And they're much closer to doing this than you might imagine. So what do we actually know about cosmology? The most important thing to remember about cosmology is that we honestly don't know the resolution to some of the problems it poses. But, as ever, that doesn't mean that we should blindly accept a mythological answer to these as yet unsolved issues. Don't try to argue that we're at all certain in any of these areas, because we're not, and you'll end up tying yourself in knots. If you're not an expert, then the best route is simply to point out that most creationist arguments about astronomy are massively flawed, and that there are large gaps in our knowledge that do indeed require work. The obvious point is that gaps in our knowledge are not the same as errors. So what don't we know? Well, we don't know the exact composition of the universe. This may seem like a stupid thing to say, but it's actually very important. After all, we can't go out and sample parts of the universe, so we rely purely on observations to tell us everything we know. This means that cosmologists, in fact astronomers in general, have to come up with ingenious ways to discern the properties of distant objects merely by looking at the light they emit. For example, we know roughly how much matter there is in the universe because we can measure the effects of gravity on large objects like galaxies. It turns out that of the matter that we know there to be, only a fraction is visible. We can account for some, but not all of that shortfall. This is the famous dark matter problem. The exact nature of that dark matter is unknown, though cosmologists are closing in on it every year. What happened in the first few moments of the universe? When I mentioned the Big Bang earlier, I said that cosmologists were looking at the very first second of the universe. It seems crazy to spend so much time looking at such a negligible fraction of the lifetime of a universe that's billions of years old, but in fact the first second is very important, because in this time the laws of physics acted very differently to how they do now. Not because the laws were somehow different, but merely because the conditions were so extraordinary, with the entire mass of the universe crammed into a space that was, after 1 second, only about 1,000 times the size of our solar system. I know that sounds huge, but it really isn't very big compared to the size of the universe today. There were no atoms, nothing but a very, very hot soup of energy with a few particles buzzing around. So what happened before then? Well, we'll never be able to observe any of this. Until it was a few thousand years old, the universe was so hot that it was effectively opaque to radiation, so we can't physically see anything in the first 380,000 years of the universe or so. Everything before then is reliant on our understanding of particle physics, learned from accelerators like the Large Hadron Collider, LHC, at CERN in Geneva. When we get into the first second of the universe, we're getting towards the types of energies and densities that even CERN can't probe, so we're entirely reliant on theory. Finally, one other thing we don't know is what's really out there in the universe beneath the resolution of our telescopes. For example, the question that most people want answered is, are we alone in the universe? We really don't know this and may never find out, but there are several missions in space now looking for habitable planets and attempting to detect the signature of life in the form of oxygen and other markers in planetary atmospheres. This is the real cutting edge of observational science, but it's not really cosmology, so I'll skip it here. Things we can never know. Well, there are some philosophical questions that we can never know the answers to. Some of these are the matter of intense debate, but really we don't have any way of determining the answers to these questions or even of knowing if they have a meaning, so scientists don't try to answer them. As I said earlier, cosmology really doesn't have anything to do with evolution, but if creationists want to claim that the Earth and the entire universe is only 10,000 years old, then there are real implications for cosmology, because what we learn from cosmology is that the universe is very, very much older than this. How do we actually know this? Well, astronomers look at objects in different scales. So, for example, some astronomers look at nearby objects like variable stars. Variable stars are what's called a standard candle. That means that they follow well-known laws. If you can see how quickly a star is varying, then you know roughly how bright it is. And because you can see how bright it appears to be, then you can compare these two and you can work out how far away it is. So variable stars are a very good way of measuring distance. We can see them out to about 50 million light years. So this gives us a minimum age of the universe of at least 50 million years, which is already 5,000 times older than the creationists believe it to be. What about the oldest visible stars? To find this out, we can look at objects called globular clusters, which are clusters of thousands, tens, sometimes hundreds of thousands of stars, all tightly held together by their own mutual gravity. Now it turns out that stars age at different rates. The larger a star, the more massive, the shorter its lifetime. So therefore low-mass stars like our Sun, or even smaller, age quite slowly. Our Sun's expected to live for about 10 billion years. But lower-mass stars still can live even longer than that. We can look at these globular clusters and inside them we see stars that are up to 13 billion years old. And that's based on well-established stellar models, that is, computer models which predict exactly what these clusters should look like at given ages. So right there we've got the minimum age of the universe to at least 13 billion years. That's over 1 million times older than the creationists believe it to be. What else can we do? How else can we put limits on the age of the universe? Well, we can learn from white dwarfs. That's another kind of star. White dwarfs follow a very well understood pattern of cooling. Also, because we know exactly how these objects are formed, we know what temperature they started at. So therefore, if you measure the temperature of a white dwarf, you can tell how long it's been cooling for. And it turns out that some white dwarfs have been cooling for about 13 billion years, and this is based on very well understood laws. So just by looking at the nearby universe, we can tell that the universe is at least 13 billion years old, which is actually pretty close to its actual age, which is a little under 14. What about the cosmological arguments? Well, we can measure distant supernova. A supernova is an enormous explosion that happens at the end of the life of a very massive star. Supernovae are another kind of standard candle. That is, we know exactly how they form, and therefore we know how bright they should be, so we can see how bright they appear to be, and that gives us the distance to them. The most distant supernova we've measured so far have been about 11 billion light years away. So that tells us that the age of the universe is at least 11 billion years old. So we've got a totally separate confirmation of a very old universe with a totally different technique. We can also directly measure the expansion speed of the universe. In an earlier slide I talked about the Big Bang and how we know that the Big Bang occurred because we can see that galaxies are all moving away from each other. Of course, we can measure how quickly they're moving away, we can reverse the clock, and then we can estimate how long they've been moving away from each other for. And that's roughly 14 billion years again. All of these different techniques are homing in on exactly the same number. In fact, cosmologists now agree that the age of the universe is about 13.8 billion years. Another problem confronted by cosmologists is large-scale homogeneity. That is, the universe seems to be pretty much the same everywhere. From your earthly perspective here, if you look in all directions around you, the universe seems very different indeed. But if you start looking at larger scales, much larger even than our own galaxy, then it starts to seem very similar, regardless of where you look in the sky. Starting in the mid-1960s, scientists discovered that there is a background radiation to the universe. That is, the remnants of the Big Bang, a kind of cosmic afterglow. Once scientists started to measure this background, they noticed something very strange about it. That it was not just very similar in every direction, but almost identical. It varies by about 1 part in 100,000. That's like building a swimming pool a metre deep, where the depth of the water varies by no more than 1/10 the thickness of a human hair. Of course, this caused problems for cosmologists until they realised that the only theory that could possibly explain the origin of this background radiation was the Big Bang. Now, there are extra tweaks to the theory required to explain exactly why the universe is quite so similar. After all, the cosmic microwave background dates from a time when the universe was hundreds of thousands of years old, so there's no way that all parts of it could be in thermal contact with each other to exchange heat and remain at the same temperature. So how exactly is the background so similar in every single direction? One of the proposals made to explain this is a theory called cosmic inflation, which proposes that the very early universe expanded much, much faster than it does now. There are other theories, of course, of increasing complexity, which are mostly beyond the scope of this talk, though I will cover one of them on the last slide. But there's still more to discover about the cosmic microwave background. This background glow dates from the very early days of the universe, when it was still cooling down. These tiny fluctuations actually tell us a lot about the uniformity of the early universe. How homogeneous was it back then? And more than that, based on measurements of these fluctuations, we can actually build models of how structure arose in the universe and show exactly how these tiny perturbations led to all the galaxies, stars and planets that you see around you today.